All right, let's go over this review. We're going to just go over the free response right now. So this was a problem where we were talking about the two different treatments, a low-dose aspirin and a placebo. So I did P with a little l as being the proportion of people who take the low-dose aspirin who develop colon cancer. That's what we're testing. Okay, how's this treatment affecting the proportion who develop colon cancer? So P with a little p is the proportion of people who take the placebo who develop colon cancer. You have to have that who develop colon cancer in there. That's what we are testing, as that's what tells us if what kind of results we had. That's a response we're measuring. Okay. So our null hypothesis is that those groups had an equal colon cancer rate, but they wondered if this provides statistical evidence that the low-dose aspirin each day would reduce the chance of developing colon cancer. So I did it like this, that the P of L is less than the P of P. All right. So here is our conditions. So we had 1,000 people total, and they split them in half. So it is essential. It is absolutely required, no exceptions, that you stated that there were 500 people. See, they were volunteers, so they were not randomly selected. They are randomly assigned. So 500 of the volunteers were randomly assigned to the low dose aspirin group, and 500 volunteers were randomly assigned to the placebo treatment group. The reason that that random assignment is required, is essential, is because if you remember from the beginning of the year, with experiments, it is that randomly assigned to the treatment groups so you can claim the cause and effect. Okay, so that's why that random assignment, it's part of experimental design, has to happen. Okay. So then here were the successes and failures that were both greater than or equal to 10 for the aspirin, and successes and failures that were both greater than or equal to 10 for the placebo group. And for the independents, that 500 was less than 10% of all the volunteers on low-dose aspirin, and so on for the placebo. But I had quite a few people missing this still on the quiz that I graded from Monday. We are assuming that the P of L and the P of P, so the two different groups, are independent of each other. There was nobody being double counted. So this approximately normal model applies. You just have one normal model, guys. This isn't two. This is actually a normal model that is centered around whatever that difference is, whatever that difference is between these things right here. And, we're centered around zero difference, wondering if there is a difference or not. Okay. All right, so next is the two proportion Z test. Here is what I put into my calculator. It said that we had 15 of the 26, and then we have the other one, 26 of the other people. Okay, so they did tell us specifically those numbers there. And so then we were wondering, so then that was the less than. So we got a p-value of 0.034. So with that p-value being less than alpha, guys, alpha is 0.05, not 0.5. 0.5 is 50%. Okay, that's not alpha. Alpha is 0.05. Okay, so we're going to reject the null. So since the p-value is less than alpha, I reject the null. There is evidence that the true proportion who take the low-dose aspirin who get colon cancer, look, I had this bad, who develop colon cancer. The true proportion of those who take the low-dose aspirin who develop colon cancer is less than the true proportion in the placebo group. Okay, I needed to have that in there. It does appear as though taking that low-dose aspirin reduces the chance of getting colon cancer. Okay, all right, so that was number one. True, actual, that was an actual AP question in 2015. People turned the page. There was problem number 4, and then a big old blank page just like that. Okay, next, number 2. This was part of problem number 6 on the free response test. There are 6 free responses. The first 5 are straightforward, like that one was, the previous one was a phantoms, but number 6 is an out of the box thinking one. Well, I only have the part that was applicable to what we've been doing, but it always starts off with something we know, and then it goes to things we don't know yet. So this was about 2 different treatments, and one of the treatments could only be administered with a pill, and one of the treatments could only be administered with a shot. So we were first asked if this could be a double-blind experiment. Why or why not? So there were 3 things that have to happen on this. You have to answer it. And so, yes, it can be double-blind. Then you need to indicate what kind of like that you have an understanding of the definition, but don't give it in generic terms. Kind of explain to them what the criteria are to be double blind in context of this study. And that's what I have here. If neither the patient nor the person administering the treatment or doctor know which type of medicine the patient is receiving. See, that's context. Then the experiment can be double blind. And here is how it can happen. And that's the third thing that it required there. This could happen if the subjects assigned to treatment group A get the actual pill, but a placebo injection, like a saline or something. Additionally, the subjects in treatment group B would get a placebo pill and the actual medicine, the active ingredient in the injection. Okay, next is B. The conditions for inference have been met. Yay! That means I do not have to do the assumptions portion. Okay, so no assumptions. Construct and interpret a 95% confidence interval for that difference between the two, the proportion who would survive at least 15 years given treatment A and treatment B. So P of A equals the proportions of patients with this potentially fatal disease who receive treatment A, which is the pill, and survive at least 15 years. You can't just say the proportion of people who get treatment A. Okay, that's not the proportion of people who get treatment A. It's the ones who get treatment A and survive at least 15 years. That's what we are measuring. Okay, and same thing with P of B, the proportion of patients with a potentially fatal disease who get treatment B, which is the injection, and survive at least 15 years. That's the indicator we are measuring. All right, so this is a 2 proportion Z interval. Hello, people. You must tell them how you subtracted. They don't know otherwise. Okay, so I put the information in for the first group into 1 and the treatment A and then treatment B. It's not, you can't assume that it's going to be A minus B. All right, so it gave that interval. So I am 95% confident that the true proportions of patients who take treatment A live at least 15 years is between 6.74% and 23.1% higher than the proportions of patients who take the injection. Since 0 is not in the interval, this provides evidence that there really is a significant difference in those survival rates between the 2 different treatments. Okay? There you go. So that right there was the first 2 parts of a extensive problem number 6. That's the most heavily weighted problem. From here, they would then that go off in kind of like a type of direction outside of the box that we haven't ever seen yet. It's an investigative task. I can't anticipate that. But anyway, the first part is always something you're familiar with. All right, number 3, 2012, number 5. Okay, exactly straight. Oh, now this one I threw at you was a 1 proportion test. Okay, and it had ideas about errors in it. So you had to understand, of course, what this problem is talking about. P the null hypothesis equaling 0.35 is saying that the council would not fund more fitness programs, okay? But if they have evidence that it is lower than 0.35, then they will fund more physical fitness programs, okay? So here we go. So then we want to know about describing what a type 2 error is in context of this study and also a consequence straight up, exactly the way you're expected free response wise in 2012 to do. Okay? So I have to think to myself, okay, that tells me that we, you know, we think, our sample makes us think. Sorry, my bad. Sample makes us think that the proportion of people who are whatever, the proportion of adult residents in the city who are able to pass the physical fitness test. They defined what P is here. So our sample makes us think, you know, that it's still 35%, okay? When in reality, that it is actually higher. So we need the council to fund more physical fitness programs, but we did not detect that. All right. So with a type 2 error, the sample results do not show or detect that the physical fitness rate is, it says lower. I keep getting this mixed up. Okay. Does not detect that it is lower, because lower is whenever they'll fund more programs. I keep thinking if they say it's higher, they'll fund more. Okay. When the physical fitness rate is actually lower. Okay. So I'll have to go in there and fix that. All right. Then a consequence of this error is that the city council will choose to not fund more physical fitness programs when we really need them to, okay? Because we've got a problem. All right, now this is interesting. Look here. The Recreation Department recruits 185 adults who volunteer to take this test. The test is passed by 77 of the 185 adults, resulting in a huge p-value, 0.97. Wow, for the hypothesis stated above. If it was reasonable to conduct a test of significance for the hypothesis stated, meaning that like the conditions were met, okay, using the data collected from the 185 volunteers, what would the p-value of 0.97 lead you to conclude? So I'm just going to be honest. My first thought process on this, I did this question wrong. I was thinking it was asking me to interpret what that p-value means. But it's just saying, like, what would I conclude from that p-value? What you would conclude, that's the conclusion section of our phantoms test. So that is telling me what the p-value is, what it would lead you to do, and say what that conclusion means. So that p-value 0.97 would be greater than the alpha of 0.05. So I would fail to reject. So since that p-value is greater than alpha, there is not evidence that the proportion of people who pass the physical fitness test is less than 35%. Okay, so with that one, I didn't get evidence it's low. Okay, so describe a primary flaw in the study described in Part B and explain why it is a concern. You have to have 3 things to get full credit. Number 1, the primary flaw is that the recreation department recruited volunteers instead of randomly selected adults from the community. Okay, so that's the first thing you had to say, that they were volunteers, not randomly selected adults. Okay, remember how we talked about that's important. Now, because we want to generalize to all adults, then we need to randomly select from all adults. Okay, if you do not randomly select from your population, then you can't generalize to the population. Okay, and then they had to say that these volunteers, this is a concern because these recruited volunteers Most likely, you have to say why it's bad. They want to participate in this physical fitness program because they are physically fit and will do well on the test. Okay, so you had to say something along those lines, why they wanted to participate and why that makes them not representative, why that makes them not representative of the population. That's what you had to say. This sample, and then you had to say a direction, like how is this result different from the real population you're trying to generalize to? So this sample would overestimate the true proportion of adults who are able to pass the physical fitness test. Okay, so again, state what the problem was. It was volunteers, not randomly selected, and say why that's a problem. These volunteers are not representative of all the adults because they like physical fitness. Okay, and then what the direction, how it compares to what it probably should have been or would have been if you had a correct random selection of people. And so this sample is an overestimate of probably the true population amount. Okay, so there was that. Lots of things involved in getting your full credit there. And here was our last one. So this is about, this is so interesting that we were having for emergency calls, there's chest compressions, the pushing down on the chest, plus the mouth-to-mouth resuscitation. So that's interesting that in 1990s, a study was conducted in Seattle, and they were actually wondering if the chest compressions alone, so no mouth to mouth resuscitation, produces a higher survival rate. Interesting. Okay. So they tell you that they did that and they got this p value. So it says, interpret what this p value means in context of this study. So that's the 3 parts to our p value definition. So the p value is the probability of getting this sample or something more extreme if the null is true. So those are the 3 parts I have listed right here. So there's a 7.61% chance, that's the p-value, is the probability, of getting this difference in survival rates. Okay, so the difference that we got between the CC and MMR group and the CC only group. Okay, so there's a 7.61% chance that we would have gotten these specific results, these numbers, okay? Or results at least that big. If the null is true, if in fact the survival rate, so here's what the null is saying, if the survival rates for the two treatments are equal. So remember pictorially what this is saying is that if the survival rates are equal, then, and each one of these p hats is a difference, then there's just a 7.6% chance. So here's the p hat we got. There's the sample we got, the difference that we got between them. This is this p-value right here, 7.61% chance of getting that sample results or something more extreme if the data is really centered here. This null hypothesis is when p1 equals p2. Okay, based on this p-value and the study design, what conclusion would you draw? Okay, well, with that p-value, and it does tell me a significance level. So with that p-value, see there again, we are drawing our conclusion that it is greater than 0.05, so I failed to reject HO. So since the p-value is greater than alpha, there is not evidence that CC alone produces a higher survival rate than the chest compressions and mouth-to-mouth resuscitation. Okay. Errors we were wondering about. Based on the conclusion in part B, which type of error, type 1 or type 2, could have been made? And what's the potential consequence of this error? Okay. So I have to think to myself, okay, let's see. They failed to reject. So I have to think, okay, When is that? When is failing to reject an error? Failed to reject a false null hypothesis. Type 2 error, type 2 error. That's how I have to remember it. They failed to reject a false null hypothesis. Type 2 error, type 2 error. Okay, so then I got to think to myself, type 2 error. Type 2 error. Let's see, did I draw a picture of it up here? Type 2 error. Okay, so let me think. Type 2 error is that we think HO, we think this, but the reality is this. Okay, so the truth is that CC alone is creating a higher survival rate, but we failed to detect that. So we think the survival rates are equal when actually CC alone is going to be an improvement. Okay. So there we go. Failed to reject would be a type 2 error. Our sample results, so what is happening, our sample results do not detect that CC alone actually has a higher survival rate. Okay, so that's what I'm saying on that. And then the consequence is that missed opportunity to increase the survival rate for the heart attack victims. By having EMTs only administer CC, then CC plus mouth-to-mouth resuscitation, chest compressions plus mouth-to-mouth. Okay, lots and lots and lots and lots and lots of stuff on these free response questions, and every single one of them is an actual free response problem to the depth that you are expected to understand these concepts. Okay, so I hope that these help you understand the depth that I need you to understand errors and to proportion hypothesis tests.